All right, hey class, can you hear me? Online people?
Yes.
Awesome, thank you, Rai. So I am setting up the classroom stuff now. Just give me a little more minutes. I'm sorry about the late. All right, Zoom people, can you hear me now? Great, thank you. Awesome. Yep. Okay, and then I suppose Aaron, the class can hear me, of course, right? Cool. Is that clear enough? Awesome. All right. Hey guys, welcome to today's class. I'm sorry this is a little bit late, but now we can start. And let me just introduce myself real quick, just in case that you didn't see me before. My name is Tiffany, Tiffany Bao. I am assistant professor here at Sky ESU. And my research is software security. I am a colleague of Professor Adam Dopay, and we co-host this class together. And starting from today, I am gonna give you some interesting, introduction or say like, some lectures in terms of cryptography. So I'll be here for this week and probably the next week as well. So yeah, let's start our trip of cryptography. Okay, so the first thing, when we start to talk about cryptography, so tell me that if you, have never heard of this word before. If you don't, no? One, okay. You probably have some few that never heard about this word before. That's totally fine. That's why we're here. We're learning cryptography together, right? But also let me know if you have heard about cryptography before. What kind of scenario have you heard about it? Like, also, do you have any, do you know any of the applications that use crypto, like use maybe encryption, decryption, etc.? Can you give me some examples? Yes? Security? Can be more specific, like a specific application or something they're using it. They're using cryptography. So for example, HTTPS. So if you go to the website, and then usually now if you type a website, like a legitimate website, usually it's HTTPS protocol. And for HTTPS, it uses encryption. Okay. All right. And does anyone have more applications? Yes.
Wireless data transmission.
Sorry, again?
Wireless transmissions.
Wireless transmissions, yes. Yes and no. I mean, previously, wireless transmissions is not encrypted, but now, if you're in a relatively secure environment, they should encrypt your wireless transmissions. Otherwise, everyone can just, be there, eavesdrop, and know what exactly that you're sending. Yes, please.
VPNs.
Say it again? VPNs, yes. VPNs also use encryption. All right, more?
Blockchain.
Yes, blockchain. Well, I mean, blockchain does have encryption, but I just want to know, like, blockchain itself is not entirely all encryptions, because they have this nice blockchain, structure to make sure and authenticate those, votes, and also those transactions are in the right order. Okay. Yes, please.
SSL.
Yes, SSL, and that's part of HTTPS as well, right? So SSL tells you as a visitor that is the right website, like that is the right ASU website. That's not someone just impersonating ASU. So the SSL certificate tells you that what you're visiting now is the true host. All right, thanks. Those are great. And let me just check chat real quick. Okay, yes, PKI, WPA, right. So as those online people, our online friend is saying, those are all interesting and like our real life applications of cryptography. It's just like so close to us every day now. Great. Okay, and then now I want you to think about this question. Since you have touched cryptography in your everyday life, so can you give me some feeling about what kind of properties that should a good cryptography meet? So when we talk about property, you can trace this back to the CIA model that Adam introduced before, if you still remember, confidentiality, integrity, and accessibility, or say availability. Okay, so now could you give me some feeling of what kind of property that should a good cryptography meet? Someone give me some idea. So let me do this first. So for example, it must have a good confidentiality, meaning that this cryptography hopefully won't be able to broken by anyone, like an attacker, right? Of course, you want to run a crypto, or say a crypto system that really helps you to make sure secure, because you want to encrypt those messages, and you want other people, other than the one that you really want to talk to, that know exactly the plain text of the message, right? Okay, so what else that can you think about? No? That's okay. That's why we're here. But before we talk about those properties, let's have a game together. I will need someone. So can someone come up to the stage and be my assistant? Yes, please. And in the meanwhile, I saw in the Zoom chats, Fahad saying that it should be available for people who need them, right? And that's right. Okay, and in terms of the demo, you watch the demo real quick and don't have to see the camera at this point. But yeah, just give me a second, and then I will give you, oh, by the way, what's her name?
Jalen?
Jalen?
Yeah.
Okay, so hi, nice to meet you, Jalen. And I will first give Jalen the way that we're gonna encrypt this message. And also you can use this way to decrypt this message. And then later on, I am going to send this public message to everyone so that you guys, and also the Zoom people, you will also be able to see this message. But let's see, if Jillian can understand what this message say, and also if everyone else can understand this message. Okay, give me a second. Let me first stop sharing. And let me end this real quick. Okay, you're looking at a paper that you're not supposed to look at. Let me just close it real quick. All right, and then come over here, please, Sheila. All right, so this is what I'm gonna show you. So this is the the decryption key.
Okay,
And I'm gonna give you a message of that. Or do you have a cell phone with you?
I do, yeah.
Okay, can you just take a picture of it
Yeah.
so that you can use it to decrypt later?
Yeah.
Right,
Okay.
and we can forget about this one. So just like those are the words.
Yeah, okay,
Okay, yeah, and then this is the message that I'm gonna send you. Quick.
okay.
All right.
So do I like go back or?
You can stay in the stage. And then we
Okay.
can yeah, you can just stand by with me together. Oop. Nope, I'm not gonna. All right. Turn this off. Click. Again. There we go. And online friends, you also should be able to see the screen now. Okay, so here is the message. Okay, now let's try to understand this message all together. And if you also, sorry, could you remember your name again?
Jalen.
Jalen, okay,
Yes.
Jalen, and if you already can tell this messages, you can also just raise your hand and let me know.
Oh, okay.
Yeah,
It'll take me, like, 1
yes, take your time.
second. Oh, that's actually helpful. So, so should I say it if I think I know what
You
it is?
should use this.
Yeah.
Go back to this, right? So you can
So-
get the-
Is it hello world?
yes, it's Hello World.
Okay.
Good, good. Okay.
It's too easy.
Yes.
As the two U's.
Mhm.
Prepositions for
Mhm.
where it's hello world.
Yes.
It made it way too easy to crack. It's just simple click now.
Yes, exactly. But I suppose that some of you, not everyone, already see that this is LOR. Thank you so much, Jillian. Yeah, and thanks Jillian for coming over here. Thanks. Right, and then can I have your name? What's your name?
Tim.
Tim. Okay, so you see that in this game, Jillian can decrypt it, and then using I would call it maybe the key book, right, that I gave her. But also Jim can also tell this because Jim look at this word and then try to understand, okay, this is the frequency for those letters happens, in the sentence, especially if you look at F and U, it happens a lot, right? So what he tries to do is that Tim tries to map this frequency to like the English letters, right? So he says that, okay, F and U happens a lot, and then what kind of normal letters that happens a lot in our normal English? And then he realized, oh, maybe this is maybe L, or this is maybe O, and then he tries to this together, and then he realized that this is hello world. So you see that this is the way that people encrypt and decrypt message, but also Tim as an attacker can crack this crypto system so that he will also be able to know the plain text. Okay, and now here, so usually me as Tiffany, when I send this message, I send a encrypted message to Jillian, right? So in this case, then I am sending a so-called cipher text, meaning that this is an encrypted message. And then when Jillian received this is also a cipher text to her, but she can decrypt it. So that's why there is a deal over there, meaning that this is like the party of Jillian and she's trying to decrypt this message. And in the crypto system, or say in the cryptography setup, usually when this message is sent out, it is assumed that this message is through a public channel, meaning that everyone, like you guys and like those friends in the Zoom, everyone can see this message, but it's encrypted. And then attacker can also assume this. So attacker can also look at this cipher text and try to break it by decrypting, getting the plain text. And the text that original text that are being encrypted is called plain text. I will also talk about those terms later on. Okay, so now the question is, what can Eve, like Tim, right? In this case, it's Tim. What can Eve do, right? So we're in our, we call it threat model. In crypto system, we assume that that Eve can be pretty powerful. It can be, people like Tim. It can be a smart algorithm that can get those information and use computer powers to decrypt those messages. And also, what Eve can do is that, so Eve will eavesdrop the message, just like you guys, you get the cipher text. And also, Eve could probably just manipulate this message. So for example, let me back to the previous slide. So here we send this message. What Eve could do is Eve sits in the middle and change those, maybe change from D to E, or change a single bit of this message so that the entire message will be changed, right? So Eve could have this power to manipulate the message so that by the time that Jillian, or say that the recipient receive this message, it will be changed. And then using her own code book, this message will be different. And also, someone can just impersonate Alice, or say impersonate me in our game, right? So someone can say, oh, actually, I am Tiffany, and then, but maybe Tim can come over here and say, I am actually Tiffany. I'm gonna send this message to Joey. And that's also possible. So we're assuming that those are the possible attacks that an adversary, or say an attacker, can do. And albeit all those kind of scenario, a good crypto should not make this attack successful. Okay, and then let's come back to security properties. Okay, so we first talk about confidentiality, right? So we talk about if someone is gonna send a message to another people, then someone in the middle should not be able to decrypt it, should not be able to make it to plain text and understand the exact message. Okay. And then the next is integrity. So integrity means that in this scenario means that if someone tries to manipulate the message, right, like change the message in the middle, it shouldn't be successful. It shouldn't be the case like, you know, the poor cryptography I just showed you guys. So anyone in the middle can change this message so that the recipient will receive a wrong message. So that's about integrity. Okay, and then the third is about authentication. So can someone understand what authentication means before I talk about it? Can someone give me an example about authentication? No? Okay. Oh, yes, please.
Verifying that like after something is correct.
Yes, yes. And you also have something to say?
There's two-factor authentication.
Exactly, two-factor authentication, right? So authentication means that once someone sends some message, it's truly that it's come from this person. So it's like previously when we talked about the Eve can impersonate Alice, and we want to stop this happen. So here, when I send a encrypted message to someone, I am also hoping that someone using this encrypted message can recognize that this message is truly sent from me, not someone else. So it's kind of authenticate that it is me that sent this message. And then the last one is called non-repudiation. So it means that if I send a message using my crypto system or using my encryption, I cannot deny it in the future. I cannot say, oh, no, I'm actually not sending it. So when I send this using encryption, I'm also telling people that it is truly from me and it is only me that sends it. And as long as you receive this, it must be coming from me. So this is called non-repudiation. So it's like, it's a combination of authentication and integrity. Okay. And now let's start with some terms, since we're gonna heavily using those terms throughout our section, like throughout not only today, but also the following weeks. And those terms, I really hope that you can remember because we're gonna use it. And also this is just like, the right way or a scientific way where you talk about those things. And by the way, guys, I will share slides as usual. So don't feel obligated to take notes, but of course, you're feel free to take notes for your personal convenience. Okay, so the first is plain text. So back to our game. Can you tell me which part is plain text? What is the plain text in our game? Yes, it's hello world, right? Okay, and then ciphertext means that this is encrypted message. I already forgot what I really encrypted to, but you know that this string that with a lot of F and U, like those are the ciphertext. All right, and then the third is called cryptosystem. I already used this word cryptosystem in this class, but to be more specific, cryptosystem is a system that describes how to encrypt or decrypt messages. And I will have a more specific, definition for cryptosystem. And in our series, you will learn a lot of different kind of cryptosystem. So for example, RSA is a kind of cryptosystem, and we will touch that later on. Okay, and then encryption, decryption. So it's like, what we do. We transfer from a plain text to a ciphertext, and that is called encryption. And in the opposite way, if we transfer from encrypted message to decrypted message, that's called decryption, right? But here, I want to differentiate encryption, decryption with encoding and decoding. So can someone give me an example about decoding or encoding? Yes, please. Sorry, I can't hear very good.
full text, plain text, where encryption is more, not, you're gonna use private.
Okay, so you said that you try to do the entire thing. It's not exactly, but I think you're getting close. Yes, please.
Going from, would it be like going from like the number 11 to the binary?
Mm-hmm.
From 11?
Okay, yeah, going from one, you said going from a string to the binary? Is that what you say?
Yeah.
Okay, yes. So you think that is a kind of encoding and decoding? Yes, that's correct. Yes.
File compression is included.
Say that again, file direction?
Compression?
Compression? Yes, file compression is encoding, decoding. Okay, for example, like UTF-8. I don't know if you guys heard about that, right? Or say like base 64, they're all encoding, decoding examples. So the difference between decryption or encryption versus encoding / decoding is that for encoding and decoding, everyone can kind of like decipher it, or say that everyone can get the actual plain text. It's just a conversion between, you know, a kind of string or a kind of, you know, character type to another type. And then there's no like confidentiality over there, basically, right? So everyone, as long as I know that how this encryption decoding and encoding works, you can always get the decoded or the encoded text. You are like, it's public information, basically, right? But then for encryption and the decryption, even though that you know how the decryption and encryption algorithm works, you will still not be able to get the plain text, you know, even though that you know the cipher text. So that's the difference between these two terms. And I want you guys to be very clear about that, because a couple of days ago, we have a student asking me about, you know, what is the best encryption, decryption? Well, how should I design an encryption, decryption? But later on, I realized that what he or she really wants is encoding / decoding. So I want you guys to be clear about these two terms. That you know, that is pretty important to our class. Okay. Yep. And also, you know, there is more differences I listed over there, right? So it's like when I already said confidentiality. And then the other thing is that for encryption and decryption, it usually has keys. So you will need to use this key to encrypt or decrypt a message. Whereas for other different kind of, you know, decoding and encoding things, because those algorithm is public and there's no keys over there, you just do a conversion between those characters, strings, or files, etc. Okay. So here I'm having some example here. I already said UTF-8 is encoding, decoding. What about English to French? Is that encoding, decoding, or encryption, decryption? Coding? Yes, yes, encoding, decoding. And then what about RSA, if you heard about this before? Yes, it's encryption, decryption. And it's okay that you don't know about RSA at this point. We will talk about that in our future lectures. Cool. Okay. And now let's start with our first crypto system, Caesar cipher. Raise your hand if you heard about this before. Awesome. Wow, there's so many. That's great. So Caesar cipher is, I would say, is perhaps, but I will emphasize this is perhaps, it's perhaps the first cipher system that we know in the world. And the way that they encrypt things is pretty easy. So for those letters, the A, B, C, D, E, F, like they shift those letters by 3. And this is the original design of the Caesar cipher. So for example, A will be transferred to D, and then B will be transferred to E, etc. And then later on, people make this cipher system more generalized. So instead of just shift the letter by 3, you can shift the letter by any distance. You can make it, like, call it I. You can shift it by 4 or 5 or whatever value, depending on what you like. But also, of course, you need to make sure with the recipient, you know, to agree on a like a same letter, like a same distance. So that's the way when you encrypt it, the other people can use the right way to decrypt it. But now the question for you guys, I have a question for you guys is that even though, say, it's not going to be shifted by 3, so you don't know that it's 3, but you, as a attacker, you don't know the exact distance, like the I, the value of I over here. Can you still attack Caesar cipher?
Yes.
Yes. Okay, I know that you kind of already did that in our, in our game, right? So you can still do that. How to do that? Maybe the first thing that you can come up with, let's try brute force, right? Because the possible value for I is not a lot, right? You could try 1 and try 2 and try 3, and you don't need to try 26. You just need to try to enter 25, because as long as you hit 26, you're back to I is equal to 0. It's just a full cycle, right? So yes, you could try brute force, because we're lucky we're living in the English language that has only 26 letters. But if we have, say, 10,000 or even a million more, right, a million letters, we're just gonna be very expensive to crack this crypto system. Okay, and then what else can we do? As Tim mentioned, we could try to check the frequency, right? And then we call this statistical analysis. And then let me check the chat real quick. Okay, yes, as Lou said, right, the Caesar cipher can be broken by simple guess or brute forcing or recognizing the pattern. And then here, pattern means that this is a statistical analysis, right? So we can understand the frequency, but also this is also under a prerequisite that you have to have probably a lot of possible cipher tests so that you can count the frequency of each letter occurring in those ciphertexts and try to map those frequency to the frequency of the normal letters, like in English plain text. So here what you see is a letter frequency for plain text, normal English. So we see that E happens a lot, right? It's the most, basically. And then the other letters such as A or T or O, right, or I, like those vowels also happens a lot because we don't have too many vowels here. And then we're gonna use this as a part of the algorithm, and then use that to work together with the ciphertext. And the way that it works is as follows. So suppose that you already have a lot of ciphertext, right? And then according to that, you can count the letter frequency in the ciphertext. And then for every possible key, so when I say possible key means that the key is the I, so it's like starting from 1 to 25, you want to try to calculate the correlation of frequency of the letters in ciphertext and the corresponding letters in English. So for example, here, suppose that we have a character C in ciphertext, and then we have the normal frequency of characters X in English according to the chart that we just see, right? So now let's just start to calculate the value, which is the multiplication of the FC and the so-called the plain text, like according to the I, which I that you guess, right? And then you will get the according plain text. So it's like C minus I here. If you look at here, so C is the ciphertext, or C is the letter. Let's say that, for example, let's say this is A, okay? And now let's start to guess I, which is the E. So it is, for example, if I is equal to 1, now let's start from there and then let's see, okay, C is A, then I is 1, so you will get the plain letter, the plain text for letter A will be C, right? And then you will be able to get the frequency of letter Z. And then you multiply this together. And then you're gonna try that for all the cipher letters. And then you will get a value for a specific key, I, right? so that you'll be able to get phi I is equal to the sum of all letters with the multiplication of f of c times p of c minus y. And then in this case, you will be able to get all the phi I for different key, like I is equal to 0 or I is equal to 25. So after you get all those values, you want to pick those, the most values, like maybe the top 3 or the top 5, like those candidates. And then you're going to try that on your ciphertext. In this case, we found that I is equal to 23, 13, and 7 are the topmost keys that are like most likely to be the actual key. So what you're going to do is that you're going to start to try to decrypt this ciphertext. For example, for 23, you will be able to get this IYE, this message. It still doesn't look like natural. This is not actual English, right? Okay, and then let's try 13. And then you get this message. And this looks pretty normal. This is like English that we can all understand, right? And then 7 is still something that I cannot understand. So then we know that the actual key is 13. Okay, and then I got message asking how I get this again. I'm also coming back to the slides and just check with people here. Do you think that you follow this, or you still think that you need one more explanation? You're good? You need one more? Okay, let me do this again. So let's assume that we already have this message, this string, and this is ciphertext. So what we're trying to do is we're gonna try every I, every key. Here I is the key. So we're gonna try every I, but we're not gonna like try to decrypt every message according to different key. Instead of doing that, we are trying to calculate the frequency of each letter happens in the ciphertext. And also we use the frequency that comes from the original chart, like this chart, we have the frequency already. So those frequencies represent the P over here, P of X, which is the frequency of character X in English, right? And then we're gonna use FC, which we can get from this ciphertext. And then we multiply these two letters together, and then we sum those for all the letters, like from letter A to letter Z. In this case, where we'll be able to get the phi value for I, like for different key. And then we just sort those together and get the topmost keys, and then do the decryption trial. And in this way, it's gonna be less expensive than just using I, like do a brute force, like try I from 1 to 25 and decrypt all the messages for ciphertext. Okay. All right. Okay. And then even simpler, you don't want to reinvent your wheel, and there is online resources actually you can use. So for example, this is a website, and then what you need to do, just put your message ciphertext over there, and then you can just use like guess here. You don't even need to tell them what exactly the key is, and then just click the button, and you will be able to get the output, and they will tell you the exact key. Okay, question. How did you translate the numbers like 23 into letter to decrypt the message? So the way that it works is that, so for example, for letter 23, and then you start from those ciphered letter, and then you can consider this as, you have the ASCII value, and then you minus this ASCII value by 23, and then you convert it back from the ASCII value to the letter. Okay. And now let's start to talk about this term cryptosystem. So I already mentioned that before, right? And then here we are gonna have a more formal definition for cryptosystem. you don't have to remember these terms. And I mean, you need to know what Cryptosystem represents, but you don't have to remember, like, all those notations. I'm not gonna ask you questions like, okay, tell me what are the definition of Cryptosystem, but I want you to have this in your mind, so that later on, when we talk about a Cryptosystem, such as RSA later on, you will know that what are the necessary elements inside the Cryptosystem, so that you will be able to understand like RSA or different kinds of crypto ciphers. All right, so here for a Cryptosystem, let's just look at the picture first. There are two parties over there. One is Alice and the other is Bob. And now that's assuming that Alice wants to send encrypted message to agent Bob, okay? And usually when we say, encrypted message, that message can be represented as a C because it's like a cipher text. It represents cipher text, right? So Alice using an encryption algorithm, which is we use like big E, the capital E to represent. It will first have a plain text, it's just a message, right? And then to use the encryption algorithm to encrypt the message, and perhaps with a key. So here there is a KE, meaning that this is the key that Alice uses to encrypt the cipher the plain text M. And after this encryption, Alice got ciphertext C, okay? And then the ciphertext C will be then sent to Bob. And then this is a public channel. It is a dangerous place in the sense that the attacker sitting in the middle can possibly manipulate it, can possibly eavesdrop it. So by the time that Bob received this message, it's possible that the message already changed. So that's why there is a different letters. We call it C prime here, meaning that this is the message that Bob receives, okay? And then by the time that Bob receives this message, Bob will decrypt this message. And how it works is that Bob has a decryption key, which we call KD. And then also Bob has a decryption algorithm. So then Bob used this C prime, this received ciphertext, along with the key and the decryption algorithm. And then Bob tried to recover, or say decrypt the message to get the plain text, the original plain text M. Bob also may be able to realize that, okay, there's something wrong with the ciphertext. Maybe someone manipulated, or maybe it's just like getting wrong during transmission, right? So Bob should also be able to detect whether or not this message is correct or error through this decryption algorithm. And usually for a crypto system, E and D are public. Like everyone knows about this encryption and decryption algorithm. And the only thing that people don't know, so the outsider or the attacker don't know, is about the key, right? So it's like KE and KD, they are unknown. And a good crypto system for confidentiality purpose, it should be able to make sure that even though the algorithm itself are public, as long as people don't know about the key, they will not be able to decrypt or encrypt the message in the right way. Okay, and then the next, so this is like crypto system. This is the definition of crypto system. And usually the way that people design crypto system, or those normal, like modern crypto system, can be divided into two different categories. One is called symmetric cryptography, and the other is called asymmetric cryptography. And the difference between these two is that the key, the encryption and the decryption key. For symmetric cryptography, the encryption and the decryption key are the same. So basically, Alice used the same key to encrypt, And then by the time it sends to Bob, Bob should also use the same key to decrypt to get the corresponding plain text. So for example, here, Caesar cipher, what we just talked about, it is asymmetric cryptography, right? Because the way, or say the key that you encrypt the message is the same key that you decrypt the message, which is the number, like the distance between those letters, the value that you want to shift for those letters. Okay, and then there is another categories for cryptography, which we will also touch in the future lectures. It's called asymmetric cryptography. So the key of encryption and the key of decryption are different. Usually the way that it works is that Bob is going to generate a decryption key and an encryption key. And then Bob send through a public channel the encryption key to Alice. So here means that not only just Alice, but also everyone, you know, attackers can also get this encryption key. And then Alice is going to use this encryption key to encrypt her message and then send it back to Bob. But Bob is the only people that has the decryption key, right? So even though that this message is sent through public channel, everyone can see it, only Bob has the decryption key, so only Bob will be able to decrypt it and then get the according message. And usually the key that are sent to Alice is called public key because it's the key sent through a public channel and then everyone can see it. And then the key that Bob keeps for himself to decrypt message is called private key. So that is a key that you don't want other people to see. And for you guys, if you're gonna have a crypto in the future, you wanna make sure that you don't send your private key to anyone else. That should be the key that no one should ever ask you. But if someone asks you for your public key, you should always send your public to the outside because that is how a public key should be used. Okay. And if you use things like SSH or GitHub, sometimes they will ask you for your SSH public key. So you want to make sure that you don't send maybe the server's host, like the maintainers or administrators or like say GitHub, the wrong key. And also you now already have the Palm College homework, right? So in that assignment, when you log to or SSH to the system, if you're not using the browser, if you're just using SSH session to access the terminal over there, they also ask you for your SSH key, right? If you remember that. So you already know how to play with it. You know that you are not actually sending the private key to them. You're sending the public key. So I want you to just keep like alerted that once you're sending key, make sure that you don't send private key to other people. Okay, and then for pro and cons, now you know how symmetric key or symmetric cryptography and how asymmetric cryptography works. Just based on this, high level introduction, what do you think about these two different kinds of crypto system? What are the pro and cons for asymmetric and symmetric cryptography? Okay, so let me come up with the first one. One possible issue for symmetric cryptography is key sharing. How are we gonna let your friend or the recipient know and agree on a key that no one else can know about it, right? Like if I pass Jillian the message, and if Jillian is away from me, I have to tell her, I have to maybe shout, right? But by the time that I speak this up, everyone else in this class can hear about it. So the question is, how should I tell this message, tell this key to my friend so that we're gonna be upgrading the page in a secret way? All right, so that is a possible cons for symmetric cryptography. Basically, you are converting this question of how to encrypt how to transfer a message security to another question, which is how to transmit or how to transfer your key security. Okay. And what else? What else can you think of? Yes.
For symmetric encryption, if I share my key with someone else,
Mhm.
they can then impersonate me by using that key to another person.
Exactly. Yes. So if you share the key in an insecure way and other people know about this key, then the other people can impersonate you, right? Okay. And what else? No? Okay, I'm listing a couple of pro and cons here. So the good thing for symmetric encryption, cryptography is that usually the algorithm are more efficient. Like it's relatively simpler. But then the cons, the disadvantage is that how to distribute the key security. And can I have your name?
Aaron?
Aaron, yes, as Aaron said, you know, if you don't pass the key security, then everyone, it's like this crypto system is got broken. Everyone can impersonate and attack this cryptography. All right. And then for asymmetric cryptography, the good thing is that you don't have to worry about the key distribution, right? Because by the time that you distribute the key, it's always the public key. Even though the attacker knows about it, that's fine, because he will not be able to use this key to decrypt any message. Okay. But then the disadvantage is that usually asymmetric cryptography is more expensive. Just algorithm-wise, it's going to be more expensive. And also, what if someone just lose its private key? Because as we said, the people like Bob is the only person that maintain and then keep this key. But if Bob is careless, no one can save him. But for symmetric cryptography, even though that someone loses the key, the one that, you know, sharing a message with you and sending a message with you can also tell you again what this key is, because he has the same key as yours. And that's also part of the reason why if you're using, you know, like RSA or like using your SSH key, by the time that you send your public key, you want to make sure that you keep your private key. Otherwise, if you lose it, there's really no way for you to recover it. So you have to regenerate, you know, a new key and then replace your old key. Okay, so yeah, we are running quick today. So that's pretty much what we want to talk about for asymmetric and the symmetric cryptography. I will call it at the end. I'm not gonna do more today, but I want to give you guys some time, you know, to ask me questions if you want. Otherwise, that's it for today. Yes.
For something that's asymmetric, how is one that is encrypting tell the other user the key if it's a different key?
Yeah. So the question is, for something asymmetric, how can you, like, how can someone tell that this is the right key, right? So that starts at the beginning of the communication. You need to first agree on the key, like you send them some message with the key, and someone receives that, so that he knows that this is the right key. So yeah. Sure. Yes.
There's like two Tuesday session and this session.
Yes.
And they're like different lessons,
Right. Different lessons.
So should we like attend both? You encourage attending both, right?
Yes.
Okay,
I mean, if the class allowed, I mean, it looks like so, right? It's pretty empty. So yes, you're encouraged to attend both, but if you can't, just attend one, you know, in your normal sessions, and then the other one, you can just get it online.
Right, because it's like, unlike my ASU, I'm only assigned like the Tuesday section.
Exactly.
So,
Yes.
Right, so but you should attend both.
Yes. Yep.
Oh yeah, I didn't do too well on the first assignment.
Oh, actually, just let me stop sharing, just in case that your our conversation goes into that one. Yeah.